Your characteristic? No, it's not just carbonyl because we had carbonyls before. Our aldehydes and ketones. We looked at reactivity of those and they had carbonyls. So it's not the presence of a carbonyl that we're looking at that is new. We have that group in red which has a high probability of being a leaving group. So by adding a leaving group to our carbonyl, we change that functionality. We encounter a few new functional groups, and that is also then going to change our overall chemistry approach to this. Okay? So within that activity, I had you pick out acyl bromide, acyl chloride, an aldehyde, an amide, and an ester. And I wanted you to come up with a ranking for them. And the first half of that, or the first page, was having you look at just a few choice selections to try and come up with an explanation for ranking. And in theory, if you fell into the trap, you probably used an explanation that I later told you was nonsense and you can't use that explanation. Did that work? Yeah, look at that. Okay. So we need to come up with an explanation for why we have these different reactivities or why we have these different rankings. Okay? What did you guys come up with? Why is the acyl chloride so much more reactive than, say, the acid or the ester? Let's actually move to the ester, not the acid. The acid brings in another thing. Comparing the ester to the acyl chloride. Why is the acyl chloride so much more reactive? Okay, so we could look at the ability for a leaving group. Okay? And what I should have had in there, which I think was on that worksheet, that is an invalid argument, and it is one that the textbook presents, but I would argue is not a good argument. Okay? Because if we look at an energy diagram, we end up moving towards a tetrahedral intermediate. Do we have a leaving group yet? No. So making any statement about the leaving group ability at this point in the game doesn't make sense because there is no leaving group. Why is the acid chloride so much higher in energy than everything else?
Relative positive charge on the carbon.
Okay, relative positive charge on the carbon. Okay, yes. So you're saying it is more reactive because it is more positive, and it's more positive because
You have chlorine is electronegative.
chlorine's an electronegative element. I completely agree. Please tell me the electronegativity difference between chlorine and oxygen.
Oxygen is more electronegative.
So I'm not sure I understand your argument then.
But in the ester, you have resonance between.
Why do you have resonance?
Because you have the ability for the oxygen and the ester to share electrons towards the carbon.
Why can't it share electrons?
Because of the oxygen carbonyl can take electrons towards it.
Okay. So can the oxygen carbonyl and the acyl chloride?
It can do that, but the chlorine can't have more than one bond, so it can't share electrons.
And there we run into an interesting dilemma. Okay. I know that's an explanation we've been using, but can a halogen have more than one bond? Have you heard of hypochlorite? ClO minus, right? We heard of that compound? We heard of that? Yeah, those of you in lab should be able to say yes, emphatically yes, because we used it. That was our bleach molecule. Okay, so that's hypochlorite. If those of you, I can call out the tutors. What else do you have to name when we're looking at our oxy-halo compounds? We have?
That's chlorites.
Chlorite.
Chlorate.
Chlorate. And perchlorate. Okay. So I believe the argument you told me for the acid chloride not doing resonance is because it cannot have more than one bond. And to that, I raise you chlorite, chlorate, and perchlorate. Does chlorine have more than one bond in those examples? Yes. So while we can use that as kind of hand-wavy argument to say chlorine doesn't have more than one bond, it's not true. It can have more than one bond. Okay? We could make the argument, well, this is organic chemistry. We don't care about that inorganic nonsense. Chlorine can't have more than one bond. I'm pushing you to go beyond that. Okay? We can use that analysis for the rest of the semester, but right now, and officially on Monday, I wanted you to push beyond that. So oxygen, we said, has resonance, which can stabilize the carbonyl. It can do that resonance because it has lone pairs. Does the chlorine have lone pairs?
Yes.
Does it have the ability to have more than one bond? Yes. So if oxygen can do resonance, being a more electronegative atom, it still even wants to hold its electrons. Why the heck can't chlorine? Okay. And size was something that I was hinting at in that activity. Okay. Maybe a bit too softly. Okay. I thought I was hinting at it really hard. Size was really important. Why is size going to become important here? Changes the length of that bond. Well, if the bond gets longer, what happens to the ability for the electrons to be able to jump? It reduces it, which makes that resonance ability weaker. Okay? There's another important aspect in size, and one of the hints that I gave you had to do with the Wittig Yllid. Anybody remember what the Wittig Yllid looked like? Our Yllid was this structure with some other bonds. Okay? And we said we could have drawn something like this. And we said that was a bad thing to draw, that was actually not a valid way to represent the Yllid. It had to be in the negative positive. Okay? And we may have thought that was odd, and then we came up with the explanation. Phosphorus was so large that its p orbital overlap with the carbon becomes so minimal that do we get that resonance? No. Well, what's happening when we move to the chloride? The exact same thing. Chlorine is much larger than the carbon. That prevents good orbital overlap, both because we're using the 3p orbitals of chlorine and the 2p of carbon, and because chlorine is so much larger that that atom now is moving further away. So that weakens the resonance ability. It weakens it to the point that the resonance ability becomes moot, which then means, what do I need to be looking at? Electronegativity. And we might go back, well, but the oxygen has electronegativity. But before we can get to electronegativity, what must we evaluate? Resonance. And our oxygen, does the oxygen have resonance? Yes, because its size matches that of carbon, I can get good resonance. I don't care about oxygen's electronegativity at that point. Okay? Mind explosion of nuanced difficulty within this. Okay? But that's the level I want you to at least consider before the rote memorization. Yes?
That order then you're saying you have to look at?
When we look at reactivity, where do we start?
Charge.
Charge. Next is size. Next is
No,
electronegativity. Next is resonance. Next is an inductive effect. Okay? When we're looking at the reactivity of these, where are we centering our focus?
The reactive molecule.
The reactive molecule, which is what? What is the reactive atom?
Carbon.
The carbon. Okay. So when we look at the first three effects, charge, well, they're all the same charge. Size, all the same size. And then we move to electronegativity, they're all the same electronegativity. We then move to the argument of resonance. We would go through and say the atom next to those carbons all have lone pairs, which on the first superficial blush means they all have resonance, which would then mean, well, crap, how do we differentiate? We could then move to electronegativity, but that doesn't explain the acyl chloride's extremely high reactivity in comparison to the oxygens. Does that make sense? So something else has to be going on. What we then add into this argument is that chlorine is so large that that bond becomes longer, which then means what about its resonance ability? I get a weaker resonance effect. Okay? So I end up backtracking in my list. It is so large that the p orbital overlap is negligible, which means no resonance. Okay? Which then means no resonance. I can't use resonance as an argument to explain why the acid chloride's valid. What do I need to be looking at? Okay, I can move to the next thing in my list, which is an inductive effect. Why are the oxygens already established as more stable than the acyl chloride? Resonance. Okay? So we're using the same principles we've been using throughout the semester, but we now have to add in these kind of secondary orbital overlaps, which is why we talk about molecular orbitals. It's because that's what's changing when we do reactions. It's how do those orbitals interact and change their chemistry. Okay? And that's the explanation that comes out of this, and that's the explanation that makes the most sense. Okay? Which would work if we added the acyl bromide. Where would we predict the acyl bromide's reactivity to now be? Higher than the chloride. So how do we then prove our theory? We test it. We go into the lab and we test the acyl bromide versus the acyl chloride. Which one reacts faster? The acyl bromide. Everything about our theory holds true. Okay? It is that level of thought that I'm pushing for, that I wanted you to get out of that activity, because it's really going back to what an energy diagram shows, and it's that level of interpretation that can help you go through and push through this. Okay?
You say it's less stable in a sense?
Did you ask for stability on that?
So if we go through and look at stability, which of those is going to be the least stable?
Resonance.
Okay, the least amount of resonance, which would be
Acid chloride.
the acid chloride. Okay. All of the other functional groups end up following through some kind of similar pattern. Okay. The acid chloride tends to be kind of an outlier, but the rest of them should be really straightforward in an explanation. Okay. Why is the acid anhydride higher in reactivity than all the others? Doesn't it have the same resonance? Yeah, it has the resonance going the other direction, which means
Makes that carbon more.
it makes that carbon more positive. Okay? Okay? And I almost always get someone, well, couldn't you do the resonance this direction? Yes, but then what happened to the other half of the molecule? Okay? Because it's symmetric, we still have that very electrophilic carbon on the other side. Okay? When we move to the carboxylic acid and the ester, notice that they're labeling them at the same energy level. Why would they be labeled at the same energy level? It's the same resonance. It's an oxygen atom sharing electrons in. That R group, or that hydrogen, is now so far removed that its effect back to the stability of the electrophile, or that electrophilic carbon, is minimal. Okay, we don't see anything really helpful there. When we drop to the amide, why is the amide so much lower in energy than the oxygen-containing? Okay. We're comparing, again, the ability of the oxygen and the nitrogen to share electrons. We can go through charge. There's no charge difference. We start with resonance. Oxygen versus nitrogen, which one is going to be better at resonance? If oxygen is better at resonance, what does it do to the electrophile?
Stabilizing.
It stabilizes it, which means our order here should be what? Not the order it's shown. Okay? So to do resonance, what must our atom do? Share electrons. Which atom shares electrons better? Nitrogen, because less electronegative. We go to the very bottom of our list and we now have that negatively charged oxygen. Why is a nitrogen less stable than an oxygen one? Didn't we just say oxygen is better at sharing, or worse at sharing electrons than nitrogen?
Because in the amide, when the nitrogen shares electrons, you get a positive charge on the nitrogen, which also get a negative charge on the oxygen, so you get more charged groups.
We end up generating charge when we do the resonance in our amide and above. What happens when we look at the carboxylate? We end up moving the negative charge from one place to another atom. Okay? We don't generate multiple charges. We just have one charge. Every other structure generates more charge. Less charge means More stable, that is our lowest activity. Pretty much everything in the next 2 chapters centers around those functional groups and how they react with hydrogen nucleophiles, also known as hydride. Carbon nucleophiles, also known as Grignard, Gilman, and then other negatively charged carbons. Hooray. Okay. Acetylide, cyanide, the organolithium reagents. Okay. Then what else might we look at? What other kind of nucleophiles do we have? Well, no, oxygen nucleophiles. How do they react with oxygen nucleophiles? How do they react with nitrogen nucleophiles? Okay. Which, if we think back to what we just took a test on and how we organized that previous unit, it started with hydrogen nucleophiles. Then it went into carbon nucleophiles, and oxygen nucleophiles, and nitrogen nucleophiles. Guess what? We are repeating the last unit with these magically new functional groups. All of the chemistry is identical. Okay? We do encounter some weird oddities. Why might we have weird oddities? Some of these functional groups are more reactive than our aldehydes and ketones. Some of them are less reactive than our aldehydes and ketones. Does that mean we're going to change how we see see each of our nucleophiles? Yes. Okay? And that's really the new part within this section, is looking at those key differentials on how these differentiate from aldehydes and ketones. Notice within this chart, they did not include aldehydes and ketones. Where do they fall in the reactivity scheme? Pretty much right in the middle, aldehydes and ketones. Where aldehydes are higher in energy than our ketones because we can make a steric argument. We can also make an electronic argument that the ketones have carbons which have more electrons than the hydrogen of an aldehyde, which can better stabilize the electrophile. Okay. Why would they be higher in energy than the ester, amide, and carboxylate? Resonance. Sorry. Cough. There is no resonance in the aldehyde and ketones, but there are resonance contributors in our carboxylic acids, esters, amides, carboxylates. When we look at the acid-chloride reactivity and the acid anhydride, was there resonance there? No, and we got to be careful. When we reference the anhydride, you're saying there's resonance, but again, you have to keep your focus on where's your reactivity. Your reactivity is on the carbon electrophile. Is there resonance stabilizing the carbon electrophile? No. Okay. So in our top half, ketones and above, no resonance. Everything below, resonance. Right? Kind of, sort of? Your textbook does go through and look at this as a kind of a larger, more holistic thing. So they start into this kind of energy diagram thing and then start to go back to referencing leaving group ability, which is a bad concept because, again, if we look at the energy diagram, do we have a leaving group? Not yet. Okay? So trying to rank and determine which of these react better or faster using a leaving group ability is not the best argument. Okay? Why can they get away with using it as an argument? When we look at the overall reaction, can we simplify to using leaving group ability? Yes. Okay? That's why they bring it up. That when we're looking at these groups with leaving groups, this argument works out pretty well for us. Okay? So what we've got to do is compare each side of the equation and look at their reactivities. What is the most reactive thing on the reactant side? The negative charge, which is on the nucleophile. What is the most reactive thing on the product side? The negative charge on the leaving group. So if I want to decide which side of the equation is favored, I'm going to look at those two species and compare their stabilities to each other. If the nucleophile is more stable than the leaving group, what happens with my reaction? It'll shift towards the more stable, yes, which means more reactants, which means no reaction. Okay, in our grand scheme of things, nothing's going to happen. So one of the things that you're going to be needing to think about is looking at your strength of your nucleophile, comparing that to whatever the leaving group is, and saying, should this reaction occur? And that's what they're getting you to try and summarize out of this. So if your most stable is your leaving group, then what do we get? We get a reaction. That is too similar sounding of a word. I would argue you should just write product. You're not wrong. If the most stable is the nucleophile, then we get the reactant or no reaction, which I would write as NR. Kind of make sense? I keep bringing this in within the slides, and because your textbook doesn't provide a nice place to drop it in there. I think they primarily talk about it in chapter 21. Okay, but what we've got here is a summary of all of the interconversions between each of these functional groups. Because if I want to make an amide, I want to know how to get there. Okay? Or if I want to make an anhydride, I want to know how to get to the anhydride. This chart helps me figure it out. Okay? So let's step back. Whoops. If I want to make the anhydride, is it going to be likely that I'm going to be able to use an acid or an ester? Okay. Remember, where I want to end is the anhydride. Where I'm starting is the acid or ester. Okay. Reed, you're saying no. Well, actually, it looks like it's a no on the left and a yes on the right. So those of you saying yes, why? I want to end with the anhydride. Okay. I want my product here. Where's my reactant need to be to get my product relative to the product energy? The reactant energy needs to be higher. Why? It's always going to favor the lower energy state. If I want my reaction to occur, I want my products lower in energy than my reactant. So if I want to make an anhydride, can I start with the acid? No, because the acid is lower in energy than where I want to get. Okay? For that reaction to occur, my reactants must be higher in energy. So how do I get to the anhydride? I need to use the acid chloride. Okay? And that's what this chart is showing. And yes, there are some weird exceptions to that, so don't panic on it. Okay? I can go from the acid chloride to an anhydride. I can go to an ester. I can go to the amide. Guess what? From the acid chloride, I can go anywhere or be anything. Reading rain, isn't that reading rainbow? Well, I don't blame my singing voice on the cold. That's why it sounded horrible. Normally it would be great. The acid chloride is so reactive it can go any place at once. But what happens if I start at the anhydride? I can only go down. Notice none of the arrows centering around the anhydride go up. I can't do it. Okay? Everything falls down. Well, if everything goes down, how do I ever make the acyl chloride? Over there? Okay, that's somewhat useful. What's our over there? If I start with the carboxylic acid and react it with, I knew you were going to say that. Give me the name of it. Thionyl chloride, which we saw in unit number 1, to do what? Do a substitution reaction where we exchange an OH for a Cl. And one of the things that we said about that reagent, because we were primarily focused on alcohols, said that reagent is so active that it would exchange the OH from a carboxylic acid just as easily. That's how we get to the top. We have to use thionyl chloride. So what if you start with an acid and want to make the anhydride? Well, add thionyl chloride. Now you're up to the acyl chloride. How do you come back down? you can react that with a carboxylate salt nucleophile. Okay? So the arrows are very intentionally designed within this. Some of them are reversible, most of them are not. Nearly everything falls down. Okay? Questions about that? Take that as a no. Are there exceptions? And this is a real SOB. And I would argue it's not really an exception. What functional group are we starting with? An amide. And what are we ending with? Our acid. If we go back to our energy diagram, where's the amide? Down. I'll kind of also accept that. There's our amide. And where's our acid? One above. You notice that I do have an arrow in there saying that you can do that. But that seems a little bit weird, right? I'm starting at a low energy state and I'm somehow going higher in energy. And we said that's not allowed to happen. So what is going on within this reaction allowing this to occur? Okay. Well, for us to figure it out, we have to look at the mechanism. And by us, I mean you. Do the mechanism. T-butoxide. T-butoxide is too bulky. It's really there just to regenerate hydroxide from solution. Our hydroxide will attack. We'll form our first product, which is from our what type of reaction? Our nucleophilic addition. And I apologize for calling that a reaction. I should not have called that a reaction. I should have called that a mechanism. We have our tetrahedral intermediate. Okay? And all of our nucleophilic additions, particularly nucleophilic addition followed by elimination, we will form that kind of structure, a tetrahedral intermediate. Okay? You will be asked about tetrahedral intermediates, so make sure you know what they're referencing. Why is that now a tetrahedral intermediate? If we look at the carbon that reacted, it started sp2 and it's now sp3. And sp3 carbons have what shape? Tetrahedron. Go figure. That's why we call it a tetrahedral intermediate. Our electrons can come back down and they can kick out a leaving group. We have two options at this stage. We can either kick out the nitrogen or we could kick out the OH. Which of those two options should we look at? What did you just say? Thank you. Both. We should be looking at both. What happens if we kick out the OH? We go backwards. So it's a reversible reaction. Okay? What happens if we kick out the NH, or the nitrogen? Oh, I meant to have that all in red. Oh well, right? That's what we'd have. And I'm hearing a statement that that's irreversible. For that to be irreversible, we are saying that that product is significantly lower in energy than the intermediate and then the reactant. So let's go back. What functional group do we have here? We have a carboxylic acid. Because I'm lazy, actually I'll just write C, acid. What did I start with? An amide. Which one's lower in energy? The amide. Okay. Well, there were two things that were produced, and our first swing said, you're wrong. It's not irreversible. Maybe the second one will jump in and help you out. The second one is our negative nitrogen. What would we be comparing that back to? Our negative oxygen. And when we compare that one, the negative oxygen is lower in energy. Well, what does that mean? That is reversible.
Wait, which one was lower energy, you said?
Negative oxygen versus a negative nitrogen. Which one's lower in energy?
Negative oxygen.
Because?
It's more electronegative.
It's more electronegative. Everything about this says, ain't happening. we don't get product. Okay? So I commend you for getting to this point, but everything we just wrote out says your reaction fails, except when we go into the lab, what's our yield? 96%. You missed something. Okay, and you're right, I did make this argument, oh, there's exceptions. Okay, I would make the argument, there are never exceptions. There's just recognizing that you didn't finish. C acid. How is that species going to act? Like an acid. How do nitrogens typically act? As bases. How do negative nitrogens act? Stupidly strong bases. What does that negative nitrogen do? Deprotonate. What is the result? And our protonated amine. Is that step reversible? Well, let's go through and compare. I have the carboxylate here. Is it lower or higher in energy than the acid? Lower. Is it lower or higher in energy than the amide? Lower. Everything about that product says it can form. What about the nitrogen? Well, now we've gone from a negatively charged structure to a neutral structure. That should be lower. Everything about this step is screaming irreversible. Why does this reaction occur so well? Because we have a secondary reaction that's happening at the very last stages of what we would have thought of for our mechanism. That secondary reaction carried us through to a product that was now irreversible. I wonder if we saw this before, say, in the lab with maybe the chalcone epoxidation lab. Yep, yeah, we did. Okay. Secondary chemistry is a real SOB. You have to watch out for it. It's not an exception. It's recognizing that there's still chemistry to be done. Okay. We've seen this show up before, for those that looked really carefully at the homework. When we talked about acetylides and the formation of a triple bond, how many equivalents of base did we need? Okay, that was way too vague, so let's try that again with drawing it out. Okay, this shows up on that board. How much base do I need to make that product? I've got to vote for 2. Some people have talked to me about this in very particular cases, so should absolutely know what the answer is. And that answer is not 2, it is 3. Why? That hydrogen is acidic. It is more acidic than the hydrogens on our starting alkane, which means the instant I form the alkyne, it starts eating the base. Whoa, wrong eraser. Which then means I can't make more alkyne unless I have more base. Okay? Secondary chemistry came in and bit us and made sure that we had to have 3 equivalents of base to get that reaction to occur. Secondary chemistry is coming in here and ensuring that this reaction does work, even though we wouldn't expect it to, because we form a really stable product. If we go back and look and compare our final product, we form the carboxylate product. Is that what we end with? No. Okay, well, so maybe I lied, because question says we end with the acid, and we're at the carboxylate. Oh, step 2. Why was there ever a step 2? Because that extra addition of acid is required because nitrogen went in there and removed our hydrogen from our salt. We have to follow that up with a step 2 of acid. Okay? Without that step 2, we don't get the carboxylic acid. Don't look so unhappy. You at least don't have a cold, in theory. Okay? So if we looked at our free energy diagram, what happens? Our amide goes to our tetrahedral intermediate through our nucleophilic addition. We follow that with our elimination. We'd end up with our carboxylic acid and our amide, or negatively charged nitrogen, which is higher in energy than where we started. That shouldn't happen by all rights. But what then follows that up, we do an acid-base reaction, which is now so exceedingly exothermic that that's what drives the reaction. I form very little of that acid product immediately. But as soon as it's formed, it goes through an irreversible reaction. So I may have a reversible reaction up here saying I don't get a lot of product. But what happens the instant that product is formed? It is removed from solution. And according to Le Chatelier, what happens to the concentration of product if I constantly remove it? It goes up, and I continue to form stuff. Once I've got my final reaction done, I can finalize it by adding that last little bit of acid to get me to that final state. Make sense?
One of the things that I initially saw with that was I saw the nitrogen unable to act as a nucleophile due to its size.
You can start to make arguments there and adjusting the height of, and I won't point at it, I'll just draw it, on adjusting the height of that species. Okay? On if it's higher, it's potentially because the nitrogen is less substituted. If it's more substituted, it's probably a little bit lower, okay, because sterics prevent the reverse reaction. So you will see some adjustments there. Okay. The overall picture is still the same. It's not likely to happen. We can actually use this to our advantage in what is known as the Gabriel synthesis, which is really awesome because we have another named one. But for some reason, when I first taught this reaction, I was like, oh, this reaction sucks, another named thing. And now I keep thinking of it as being cool, and whenever I look at it, I'm like, oh, look at the wings. And when we finish talking about it, feel free to point out where the wings are, because I still have no idea why I see wings, but I see wings. Okay. So what happens in this? We start with phthalimide, big, massive structure, and we add KOH. What is KOH? Base. Okay. What is that base going to do? It'll deprotonate the nitrogen. And we end up generating, this is an awesome one because of how freaking big it is. We end up generating what kind of a structure? A good nucleophile. So what could I react with this said nucleophile? An electrophile. Let's just do a simple one for the example for this point. Let's do CH3. I want that carbon to be positive, but I can't formally have it positive. What should I attach it to? How about a halogen like bromine? Now what happens? I complain when you guys draw arrows like that. I'll fix it. Okay. What's the result? Right? Well, that's kind of boring. I always had a methyl group to this big, giant freaking structure. We then follow this up with another reaction, a step 3. Okay, this was a step 2. Step 3. And step 3 is a really exciting step. It's the same as step 1. We had OH minus. What does OH minus act as? A base. Is there anything acidic? Where's there an acidic atom? There's no OHs anywhere. Those are carbonyls. Where's there an acidic hydrogen in that structure? Okay, we could try and say the methyl carbon, but then you're going to have electrons go from the carbon in to form a double bond with the nitrogen. That's going to exceed the octet on the nitrogen. Okay? So we don't really have an acidic hydrogen on the methyl either. Which means how many acidic hydrogens do we have? None. Okay, well, why are we adding hydroxide then? If it can't act as a base, it'll act as a nucleophile. Where are their electrophilic sites? Are carbonyl carbons. And what happens? Attacks. Tetrahedral intermediate, followed by, in a second mechanistic step, and this is where organic chemists become notoriously lazy, we reform the carbonyl and kick out the leaving group. And all of you may be screaming, but you yell at me when I show arrows on top of arrows. Yeah, you're right. I do. And I'll probably yell at you for this, if you did it this way too, on a test. Okay? So that happens, and we would end up with
Do it again now.
negatively charged nitrogen. Ooh, that's ugly. But there's an acidic hydrogen up here. What can happen? It can deprotonate. And I would form what is apparently an unstable negative charge, but that negative charge is actually incredibly stable because resonance. What can happen now? Well, we can add an extra little word here that might tip us off. I can add more OH, and I can have another hydroxide come in and do what? Tetrahedral intermediate, followed by kicking out the leaving group. And after all of that, I end up with this diacid phthalimide thing, followed by acid workup, ignore that, and NH2CH3. Which of those products do I care about? Okay, why the diacid? I know why I would say it. If the diacid was what I wanted, why the hell did I do step 2? Yeah, could have just gone straight to the diacid. Why? Why did I do step 2? I don't care about the acid. I care about the other one. What is special about this other one? Okay, let's clear everything away. Let's say, okay, well, Mike, you're just weird, so we'll humor you for a second. It might be more than a second. How else could I make that structure? What does nitrogen typically act as? A base or a nucleophile. So if we cleaved that bond, took this backwards, we could probably start with, say, I don't know, NH2 and, or sorry, NH3 and we might look at that and say, well, doesn't that make the exact same thing, Mike? Why the hell did you do all this giant, stupid phthalimide junk? What do you mean, no, it doesn't? Nitrogen is a nucleophile. What's that? No, it does react. There was some mumbling over here. The yield of this, if I remember correctly, is ballpark 57%. That's pretty crappy. Huh. I wonder why Mike would remember a 57% thing. Because I think there were some other things in here. Oh crap, and I don't remember those percentages. I still have a nucleophilic nitrogen, which means,
24, 3, trace.
was 57 right?
57, 24, 3.
Oh, that was trace.
The last one is trace.
Trace, 3% and 20 something? 23? 24%. When we ran that reaction, we said that is a crap reaction to run because we get too many products. Right? So we said not going to do it. Okay? And we talked about this in unit number 1. And we said that really that doesn't work out very well. And actually we kind of shifted that to unit number 2. Okay? That didn't work well, but what we could use that for was to make a crap ton of this guy. And then we could do the Hoffman elimination and we could do some other chemistry with it, but we couldn't get a good primary amine product out of this. What does the Gabriel synthesis give me? A primary amine. How many secondary amines do I get? None. There's only one nucleophilic nitrogen. The lone pair on that nitrogen is not nucleophilic. Why not? It's occupied in resonance. So we use phthalimide. Phthalimide to generate a single nucleophilic nitrogen. That single nucleophilic nitrogen can then do a substitution reaction, which then allows me to get a primary amine. It is the only way, or one of the only ways, to get a clean primary amine. Standard substitution reactions do not work. You get a mess of side products. That is the power of the Gabriel synthesis. Right? By the power of, yes, Castle, Grayskull, and all. We have our KOH starting off our reaction acting as a base, followed by a good electrophile, and we're running what type of a reaction in that second step? It's an SN2. Why SN2, not SN1? Why does it happen in the same step? Something to do with the negative charge making that nitrogen? Why is it SN2? We don't care about leaving groupability right now. You did not just mention carbocations. Carbocations are SN1. SN2. How do we know it's running an SN2 reaction? Negative charge species. That negative charge species is acting as what? A nucleophile. What is a negatively charged nucleophile defined as?
A strong nucleophile.
There it is, a strong nucleophile. Eventually the train comes around. A strong nucleophile is only important in which mechanism?
An SN2.
The SN2. That's how we know it's an SN2 reaction. That's it. Yay! Yeah, I can accept that. KOH in the next step acts as
I didn't hear your question.
KOH in the third step acts as that could have been the line for a base, but it was a nucleophile. It's what then attacks and kicks the nitrogen thing out. Okay? So the Gabriel synthesis is kind of cool because of that. Okay? That's what we end up with our product, our primary amine. It's very hard to get our primary amines. Notice that our yield here is still pretty crappy, but we don't get all the other stuff. So purification-wise, this is a lot easier. Okay? So why? Oh, here's all the questions that we could ask about it. Why do we need it? We don't have a good way of making primary amines. Gabriel sets this up for us. Okay? The ammonia and the alkyl halide, that's the one we just went through. What was the problem with it? Made a whole bunch of other products because the nitrogen can continue to act as a nucleophile. Okay? Is there another way? So this is a harder question. Is there another way of getting the primary amine without going through ammonia and an alkyl halide? That is a challenging question. In the synthesis activity that you guys have been working on, okay, a suggestion was made to do just the standard substitution, which is fine. I would argue that you have a better method. How can I get a primary amine without doing the Gabriel, without doing the substitution?
Could you have a secondary amine with a double bond and put it next to palladium with hydrogen?
Secondary doesn't quite fly with me. I know. Picky, picky, picky.
That's me too.
No. No. What is the name of this functional group?
Amine.
Still no.
No, it's not.
The imine. If I end up with a primary amine, I can reduce that using H2 and palladium or whatever I want. That will get me the primary amine as well. Okay? That does get me decent yields. Being able to get the primary amine, that may be another separate issue, and you can deal with that on your own. Okay? And because that doesn't show up on the slides, if you want to take notes on that, you can write that one down. Some people are still writing, so keep kind of recording.
Which one's easier to do?
It's going to depend on the situation.
How expensive is it to
Yeah,
make the
which is
amine?
cheaper?
Probably where I would argue your cost is probably going to come in with palladium versus phthalimide. Phthalimide is a relatively cheap, easily available compound, I believe. The palladium, even though it's being used as a catalyst, is still going to be expensive. You have to be able to pump in hydrogen gas, that special equipment. You don't need that special equipment up there. Okay? So the Gabriel is probably the better synthesis in that respect. But again, it's going to depend on the conditions you're trying to aim for. And I can't remember, so there's that as your reminder. Oh. Okay, so here we can take a minute. There's the Gabriel synthesis. Does anybody see wings?
See him at the beginning.
On the oxygens?
Because like Gabriel's the angel. So I keep associating the angel with this and seeing wings. I don't know how that works, but it does, and for some reason I can get this now.
Is it seriously named after like Gabriel the angel, not like
No,
Emerson
I think
the
it's
Gabriel?
named after a person. Yeah.
Gabriel's.
But that just happened to be how it stuck for me.
Okay.
Alpha halogenation, okay? We've seen this, Unit 1, and on Unit 2 exam, actually. If we ran this reaction as shown, what's our product? As a hint,
Bromine with alcohol? No.
Would you add just a bromine?
yeah, I just add a bromine.
Substitute.
I do a substitution, okay? Why can I get away with that substitution? First thing I'm doing with that hydrogen is, don't tell me acid base, but you're right.
Wait, what? Kinetic versus halogenation.
We do the keto-enol tautomerization, which gets us what? A nucleophilic carbon, which can then react with our electrophilic bromine. And that says electrophilic somewhere in there. And gets us our final product. What happens if we ran this under a base catalyst? Instead of going through an acid catalyzed keto-enol, I said base.
We get
I get the poly substitution for my product. Whoops. I get bromines fully substituting in that position and at the other one. And the reason why was as soon as we add a halogen to our structure, The alpha hydrogens become more acidic, which means I generate more nucleophile, which means the reaction snowballs through. Okay? Which I'm pretty sure was on the second exam. I think there was a multiple choice on it, using chlorine. Okay? Oh, it was under acid conditions? Okay, so I lied. So I might need to look at that question closer. Remind me after class. So one of the other, when we looked at this first thing, or this, the haloform reaction, or the alpha halogenations, I threw this reaction at you and said, don't have to stress about it right now, but we will see this eventually. It's a really important reaction. You got to watch out for it. Okay? What happened in this case? Okay. I do the full substitution at that methyl group with bromines because I'm under a base catalyzed ketoenol tautomerization, or keet. Look at it, keet. Our bromines are electrophile, and we would end up with that structure. What can you tell me about bromine? Bromine is a good leaving group, yeah. It's also electronegative. It's pulling a lot of electron density on that carbon. Carbon with 3 electronegative elements is not a stable, happy structure, and it starts to call for electrons. Where can it get those electrons from? Can actually get them from the carbonyl structure, and it sucks the electrons away from that. Okay? Because we have a decent leaving group in that case. It's not the greatest, so something has to force it off. Well, I wonder if I had anything to force it off. Say like a decent, strong, negatively charged nucleophile. Still have that hydroxide floating around. That hydroxide generates a carboxylic acid, a negatively charged leaving group, which means acid-base reaction, which is where the end of step 1 occurs. I would then follow this up with step 2 by adding H+. The H+ will go ahead and protonate, and I'd end up with my final product.
Question.
Yes?
Do you form the tetrahedral under this case, or do you actually form the...
Actually, good question. I did not draw it like that. I won't ask you that because I don't know the answer to that. I'll figure that out. I would guess yes. You should always form it. Why should we form the tetrahedral intermediate instead of forcing the leaving group off right away?
Because you have less charges. Or...
No. The leaving group is attached to the structure with what electrons? Or electrons found in what? A what kind of bond? A sigma bond. If I form the tetrahedral intermediate, what bond am I breaking? A pi bond, which is higher in energy, pi or sigma? Pi bond. You should always form the tetrahedral intermediate because you're breaking the weakest bond. That's why we show it. Okay. This reaction in and of itself isn't a huge issue. Where this typically shows up, though, is actually with this last kind of question on the ACS. They're famous for asking this one. Which compound will give the yellow solid HCl3 when mixed with iodine and sodium hydroxide? So if we kind of backwards work our way through this, we're saying we take sodium hydroxide, so really OH minus, and then iodine, I2, and we form HCl3. Well, as we just found out when we used the halogen, or used the bromine, we had HCbr3. So likely our other product is a carboxylic acid. Okay? Right? How did I get that carboxylic acid? Where did it come from? It came from a carbonyl with an alpha hydrogen, okay, or alpha methyl group. That alpha methyl group is what can get deprotonated by the base, reacts with the iodine to give us our HCI3. So what you end up looking for as your structures would be a variety of functional groups: aldehyde, carboxylic acid, a ketone, an ester. Okay? With really no seeming rhyme or reason behind it, until you recognize that what this reaction is useful for is what's known as a classification test, a very quick and easy test for the presence of methyl ketones. Okay? If you see that yellow precipitate, it's a methyl ketone, or the methyl ketone is what you started with, rather. Okay? It's a really popular ACS question. Okay? It goes in the vein of, did you do lab chemistry? And in particular, did you do qualitative analysis lab chemistry? Which for those of you in the lab, yes, you are. You'll be doing that for the next 3 weeks. Okay? Those of you not in the lab, that's why I'm addressing this, because it's not something you typically see. We saw another one earlier this semester that was a classification test. The zinc chloride, which was the testing for alcohols, also known as the Lucas test. Okay? Sometimes they give you the reagent, sometimes they give you the name and the classification test. If they give you the name and the classification test, I personally give the middle finger to the exam and I move on. Okay? If they give me the reagents, then I'll work through it. Okay? And yes, I've been known to give a middle finger to inanimate objects on multiple occasions. We've got our full mechanism. Oh, there we go. Hey, should have just hit next. There's your answer, Tyler.
Sweet.
Tetrahedral intermediate. Yes, you should form it. Okay. Oh, what? Okay. Sorry, I thought something else was going to pop up. Hydride nucleophiles. Kind of a fun little place to go. What did our hydride nucleophile do? Attacked the carbonyl, and it gave us what? An alcohol. And what type of a reaction? Maybe you just said it?
No, that's it.
No. It is tetrahedral, but it's not an intermediate. Yes, it is an addition. Fair enough.
Nucleophilic addition.
Keep going. Why would they be listing oxidation states? Oh, because it was a redox reaction. It's also classified as a reduction because what happened to the oxidation state? It was reduced. We went from a +2 to a 0. Okay? How does the presence of a leaving group change the reaction? Okay?
Is it going to increase the oxidation state?
Yeah. Our leaving group does change the oxidation state. That's an interesting point. I had not considered that. What would we expect our product to be? What does the hydride react with? The carbonyl, and it would reduce it to an alcohol. So if we just said same basic pattern, what might we draw as a possible product?
Just the hydrogen with the carbonyls.
Right? We just made an alcohol. Okay, some weird faces. Good. Okay, we don't like that. So if we broke down the mechanism a little bit more, our hydride comes in and attacks, breaks open, and in the case of our aldehydes or ketones, we'd have that negatively charged oxygen, so we're up at the top figure now, that negatively charged oxygen, can it come back down? Can we reform the pi bond? In the top one?
Oh, the top window.
We'd be kicking out hydride, we just put that on. That doesn't make sense. We'd be kicking out a negative carbon. Both of those horrible leaving groups. No chance in hell. What happens in the bottom case? I do have a leaving group. I could have the electrons come back down and kick out the chloride, okay, which is a decent leaving group. And I would end up with, I think I miscounted carbons. Nope, I got them. With a Cl minus. Would I think that is a reasonable thing to do? Well, I'm starting at H minus, and I'm going to O minus. Is that a favored reaction? Yeah, oxygen's better than hydrogen. To Cl minus, which is even better. Everything about it says, yep, yippee-ki-yay, go for it. Anybody see an issue with that last product? And on that note, we're done.